Hey everybody, welcome back. Mr. Smith here. In today's deck, what we're going to do is take a review of vector operations. We're going to start with a navigational coordinate system. We're going to talk a little bit about how vectors add and how to break them apart. And you're going to find this probably a pretty useful foundation for the discussion that we have in Giancogli's chapter 16, where we do end up doing some pretty hairy vector addition problems. So let's just dive in here and grab our first slide where we review how the navigational system works. If you're like most people, your teacher taught you that this out here is 0 degrees and this right here is the first quadrant when you started learning trigonometry. So that knowledge just look good. Let's build on it. This direction up here, which we call north or up, that was the 90-degree direction. West or that away is 180 degrees. And then down or south we call 270 degrees. So directions and angles, they go together. Also, it's really handy to remember the numbers of the coordinates. I think everybody remembers those, 1, 2, 3, and 4. The big thing to remember, though, that's built into this is that when we're giving a direction to a heading, let's say it's somewhere out here, that what we do in numbering the directional angle is we start at 0 and we rotate counterclockwise until we match up with the vector direction itself. And so the direction that we'd tell everybody this angle, this vector right here was going, would be 90 plus whatever this little theta dude is right in here. So 90 plus theta. You'll see us repeatedly do a couple of kinds of thinking as we situate vectors. And what I want to do is just have you tip you off. It's really a good idea to keep in mind 0, 90, 180, 270. Keep those in the back of your mind and be flexible and be willing to do a little bit of mental math because what you want to end up with is a good quality picture. Believe it or not, even in the world where we all have calculators, it's important to get a good quality diagram for these so that you don't get wrapped around the axle and make a silly mistake with missing up x and y, for example. Okay? All right, so we're going to dive in and talk about 4 different examples. And we'll start at the shallow end here. 10 newtons at 40 degrees, I've pre-drawn the answer. This to me is a really easy example because it's in the first quadrant. It's naturally intuitive to say, well, here's 0 degrees pointing out east, and I'm just going to rotate until I get to 40 degrees, and very few people make a mistake drawing that vector. There's my vector. Right. The big thing I want to remind you of is that, at least the way I teach it, I picture the vector resultant, the answer, as an arrow that's pinned down at the tail. And what I can do is I can rotate this guy freely back and forth. And what I'm going to do is just rotate this guy 40 degrees, boom, done. I draw my arrow in. It's perfect. But the bit that I mentioned about being flexible with your mental math comes in handy when you get one like this. So I've pre-drawn the answer, 10 newtons at 260 degrees. But here's how you'd get there, at least the way I think about it. Also, I'll say more about it in a second about the goal that I have in doing my drawings. But we'll start out with 0, 90, 180. To me, it's easier to think about. 260 is pretty close to 270. So if I draw 270 and then back this guy off by 10 degrees, then I've got the right direction. Okay, so the second part of what I was going to say is that I always try to draw my vector addition pictures so that they're very clear and that the 10 degrees looks like a 10 degrees. The biggest thing that students do wrong is they tend to draw ambiguous triangles. So they're just going through the motions with a picture. And everything looks like a 45, 45, 90. It's some generic vector picture. But it sets you up so you get x and y potentially mixed up with each other. And it's not supposed to be hard, but that's the thing that happens. So here's one that we're going to do from scratch. I have 10 newtons at 210 degrees. So to me, as I think about the 210, I'm going to run through the mental math of thinking 0, 90, 180. 180 plus 30 would be 210. So in my head, 210 is 180 and then a little bit more. That to me sounds easier in my brain than going all the way to 270 and backing off by some amount. Okay, so this, again, 210 looks naturally like 0, 90, 180 plus 30. And then I'm going to put my pivot here, has always been there, and I'm going to draw the vector right there. and the interior angle that I'm going to work with when I do my trig is 30 degrees. Okay? That business of going past something and backing off, though, it comes in handy. So the big thing I'm after, again, is to make the interior angles clear. I also like my interior angles to always be 45 or less because they make my diagrams easier to work with. So when I see 340 degrees, I'm going to imagine that 340 is pretty close to 360. So I imagine going all the way out to 360 and then backing off by 20. And so I'm going to draw that vector right there, and it's very clear to me right now that this is 20 degrees. Okay? And so that's how I think about quadrants in navigation. It helps to be handy with a little bit of mental math. Okay, so let's go and take a look at a simple adding vectors example, and we'll take a little review here. The idea of me putting the small angle inside the triangle fits with the thing I'm going to say right now. When I draw components, which is what these are, and I work to add them, I always draw the long one first. So here's a little review. I'm going to start here at the origin. I'm going to draw 4 meters heading out this way, and he's heading east. Okay, so here's my 4 meters. Then, by the rules of vectors, I can't come out here and draw 3 meters going south, or rather 3 meters going south from here, because that would cause, it's not a correct way to add vectors. You have to add them tip to tail. So the tip of the first one has to feed into the tail of the second one. And I think what I'm going to do actually is snag my eraser here and get rid of it. I shouldn't have put that 4 in there. It kind of makes it messy to look at. So I've got my 4 meters up here. I've got my 3 meters here. And they're all fitting together like one-way streets, which is the way I talk about them. The resultant is going to go from the beginning, the origin, to the end, right there. And I'm going to think of 2 things now, 2 math operations. There's Pythagorean theorem, and then there's sine, cosine, and tangent to figure out the angle. So let's do Pythagorean theorem first. I know you guys that are sharp are paying attention. You're saying, oh yeah, that's a 3, 4, 5 triangle. You're cheating. And I totally am, because I don't really want to reach for my calculator if I don't have to. In certain triangles, you just memorize after a while. So C is going to be equal to the square root of 9 plus 16, which is the square root of 25, which is indeed 5. Okay, so that checks out. What I'm going to do then is call this theta. That's my interior angle. If you want to end up with answers that are identical to mine, then what you're going to do is use the given parts of the triangle in this step right here. So tangent of theta is equal to opposite over adjacent. So opposite of theta is 3. The adjacent to theta is 4. So tangent of theta equals 3 over 4. And then into our calculators, we'll plug something like this. Theta equals tan to the minus 1 of 3 over 4. And what that's going to do is it's going to give me theta equals 37 degrees. And we're almost home free. What's our displacement? Well, it's not going to be 5 meters at 37 degrees. What we have to do now is have that flexible thinking. It's in the 4th quadrant. So what I'm going to give them from a navigational angle is going to run something like this. Here's 0, heading straight out east, 90 is north, 180 is west, 270 is south. This is going to be all of those put together plus whatever this mystery number is right here. So because I already know the theta, though, it's easier for me to say, well, if I just go 360 and back it off by 37, that's my answer angle. And so the answer is indeed going to be 5 meters at 360 minus 37, which is 323 degrees. Okay, so keep it in mind, adding vector components. Second thing you can do with vectors is you can break them down, you can resolve them. And this is the flip side skill. You have to have both of those skills to be able to do stuff. So 10 newtons at 340 degrees, this is another 4th quadrant guy. So we're going to draw 340 degrees to me is the same as going to 360 and backing off by 20. So I'm just going to draw this pencil this in right here. Here's my 20 degrees. And there's my vector. So this is why I like all of my interior angles to be small, because the act of resolving vectors means you have to visualize a right triangle. And if you're doing it right, the right triangle fits so that this arrow tip right here extends out from the origin just as far laterally as the angle or the vector that you drew, the 10 Newton one. And then you're going to drop down a second vector into that so that this angle that you draw right here is always a right angle. That's easier to do if this interior angle is small, so less than 45. So that's really the logic behind what I was trying to suggest to you. So anyway, what we're going to have here, our resultant is 10 newtons. I'm going to call this component over here Fx. We've got this component over here is Fy. And we're going to get to work with our trig. So Fx is going to be the adjacent of our triangle. So we'll start with cosine of 20 degrees equals adjacent, that's Fx, over hypotenuse, which is 10. And we'll go to the calculating machine, and I worked this one out before. That's 9.4. And then we're going to pull up the sine function, and the sine of 20 degrees is Fy over 10. And that gives us, I was kind of sloppy up there. What I should have done is go like this. Gives us that Fy equals 3.42, I believe. Just double checking. Yeah, that's right. 3.42. And then this one was Fx equals 9.4, but you knew that. Okay, so that is having done all that thing, resolving that vector. Resolving the vector comes out with Fx is going to be 9.4 units east. And I should, hold on, let me not be so sloppy. I want to give units on this whole thing too. So it's 9.4 newtons east plus, plus will work, plus 3.42 newtons south. Okay, so there you have it. That's resolving unit vectors. Hopefully that clarified and didn't make things worse, but there you go. So that's our little review. There are further reviews that delve deeper into this if you want them, and I can give you the link for that if you're interested. Okay, but thanks. Take care, and we'll see you in the next video for the things you really need to know, which is how to use unit vectors to do complicated vector operations. Okay, bye-bye.